Yes. Good evening, all from the ISHE student chapter of Shastra. So this is the 17th G Meet talk from one of the first batch that I handled upon joining Shastra from the 2013 batch. And we had 16 talks before, and this is the first time we are going to have someone as a Dr. Nitish Govindarajan. So I'm very proud that the student whom I had opportunity to teach during my during his undergraduate days has now went on to finish his masters in US and then moved on for PhD under a very prestigious Shell program in University of Amsterdam. Finished that, and now he is a postdoc at Denmark. The group in which he has joined for postdoc is one of the very well-known, very well-established catalysis research group. In fact, when Nitish told that he's got an offer to join that, I immediately wrote back that 10 years before, when I was about to end my PhD, when I used to read something else apart from CFD also, there was a seminal paper on catalysis, how to fine-tune the catalysis from the research group that he has joined now. I could just recollect that. It is that kind of very fresh, very well-known, very authenticated research group. So I'm very happy to have with us Dr. Nitish Govindarajan from the 2013 batch. I think the first in the G Meet series to have someone, an undergraduate from Shastra, whom I have seen growing up with enormous experience across universities in 6 countries. So thank you, Nitish, and I'm very happy to have you here. So you can continue.
Yeah, so thank you so much for the kind words, Professor Naren, and also I'd like to thank you for initiating this G Meet series. I think it's a great way for us to be in touch with the current students and also with other alumni and exchange our experiences and learnings, and hopefully that's beneficial to people. And also I'd like to thank you for giving me the opportunity to talk today. So I have a presentation. Let me try to share.
Yeah, you can share it.
Yeah, it says there's some permission issue.
You're not able to share it? I think Nitish just moved out, and I think suppose he will join.
I think he's just restarting the application, sir.
Yeah.
Because once you get the permission, I think you need to restart.
But I think he is already invited, so he does not require as such permission. Just
Yeah.
let me see. Yeah, Nitish, is it sharing?
You see my screen?
Yeah, I think it will begin. You have to just wait for a moment. So in the present now, like you are sharing that. You click present now, and you shared your entire screen, huh?
Yes, sir. Can you see it or no?
No, I'm not able to see the screen.
No,
right now?
Now it is presenting. Yeah, it's presenting. Wait.
Yeah.
Okay. So you can see the title and the screen, right?
Yes.
Yeah. Okay.
Yes.
Thanks. Yeah, great. Okay, so the title of my talk is Career Catalyzed by Silicon, and I hope the reason that I chose this title will be clear during my talk. So what I want to do in the next 30 minutes or so is just to share my experiences since I graduated in 2013, and to the different places that I have had the fortune of being in. So over the past 7 years, which is actually a really long time, if I think about it, time just flies. So these past 7 years, there have been a lot of experiences I've had, and I'd like to share all of them with you. So I'd like to begin actually with 2013. So in my 8th semester, I had the opportunity to do a semester abroad, like for my final year undergraduate thesis. So I think that's still there right now. You can finish. You have the option to finish coursework in the first 7 semesters, and then you can spend your entire 8th semester doing your project. I think that's a great way to work on your project with sufficient time. So I had the opportunity to visit Germany when I was in my 8th semester. So I spent about 4 months at the Institute of Technical Physics at KIT. So KIT is a university that's located in a place called Karlsruhe, which is in the south of Germany. And my project was actually a combination of using experiments and simulations to understand mass flow sensors for cryogenic applications. So it was really nice that my project had both experiments and simulations, because that was very helpful for me to decide what I was really interested in. So I actually decided during this project that I would never want to go into a lab again, because I really didn't enjoy doing experiments, and that if I wanted to further continue my path in research, I only wanted to do simulations. So I think this was very helpful for me to make that decision. And it was also the first experience for me in an actual research environment. So before this, I had only done a small internship, and this was really the first time I was actually in a research lab. And the institute that I was in, they were full-time research staff, and so it was really good for me that I had such an experience in my undergraduate degree. And also, apart from all of these scientific aspects, I think one of the things that's very important is also the practical learnings that you can get by going to a new country. So I think there's a lot of things you can learn, which can be very invaluable. So for instance, one of the things you can do is to interact with different people that belong to different cultures and different backgrounds. I think that can really help you open your perspective and widen your perspective when you talk to these people that come from different cultures and backgrounds. I think that's something that everyone should try to do. I think that's one reason why traveling is really nice, because you can get to meet all these people from different backgrounds and have conversations with them and widen your perspective, because you might have been brought up in an environment where you are used to thinking in one way. I think it really helps to have wider perspectives and talk to different people that have have grown up in different environments. Another major challenge. So this was the first time I was actually going to a Western country, and it was also non-English speaking. So there were challenges associated with food and language. So with food, for instance, at least 7-8 years back, Karlsruhe is actually not a very big city like Berlin or Munich. So it wasn't that difficult. It wasn't that easy for me to find, for instance, vegetarian food. And I'm sure you can also ask Professor Naren about his experience when he was in France, because I remember him telling me about how difficult it was for him to manage with food. And I also had some difficulties, and that's when you learn to try, new cuisines or try to cook yourself. And I think all these skills are very important if you want to spend, significant time abroad in your career. So also language is another important thing. So in Germany, not many places people know and speak English. They actually prefer speaking in German because they're just more comfortable with it. And so if you plan to stay in a country for a longer duration, so it might not make sense if you're just going for 3-4 months, but if you plan to spend 4 or 5 years in a country, then I think it makes a lot of sense to try and learn the language because it can help you integrate with the society a lot better. So you can have small talk with people when you meet, whoever you meet. It's a lot easier if you talk in the local language. And it also I mean, they also appreciate it a lot because it shows that you're putting an effort to try and integrate into the society. So I mean, as if you just want to stick to the university and like having friends in the university, it's okay to just know English. But if you really want to integrate into the society, it helps a lot to just know at least basic language, mainly in Europe, because in the US everyone speaks English. And to me, this was a great teaser for my master's. So I had already decided that I will be doing my master's abroad, and I think this experience was really like a teaser for me to how life would be if I moved abroad. I think this, in that sense, it was really great. And what I would like to say is that people should definitely consider doing the semester abroad program. But then I say, put a star here, which is conditions apply. And I say that because you have to think about a few things. So at least when we were there in our batch, we had a lot of options to go abroad, but then a lot of them were like mostly doing coursework in some universities in the US where you have to pay a lot of money. And for that, you have to think a bit, because I don't think it's very useful to do coursework. I don't think you'll learn a lot. And also you have to spend a lot of money. So you have to think if you can afford to do that, and if you would rather save up that money to do your master's. The other option is to just go to university and just do research, in which case you don't have to pay any tuition, you just have to pay living expenses. So in that case, if you can afford to do it, maybe it's a good idea to do it. But I think the best option would be, so for instance, in the case of KIT, they actually give you a monthly stipend, and that can, that is enough to cover your living expenses. And also I was able to save some money to travel around Europe. So if that's the case, then I think it's a very good opportunity, and you should definitely consider doing it. Although, I mean, this year is probably not the greatest of times, but probably from next year onwards, things get better. And then I think SAP is like definitely something you should keep in mind if you have ideas of pursuing masters abroad. After that, I moved to the US. So I moved to Carnegie Mellon. So I started my master's in Carnegie Mellon, which is actually a university that's located in a place called Pittsburgh, which is in the East Coast of the US. Most places in the East Coast in the US, you have to think a bit because the climates can be really harsh. So I still remember that during the winter that I was there, temperatures would go to -30, -35. So you have to be ready to withstand such temperatures. It's a lot better if you go to places like Florida or California, because the weather is much less. It's like much better, much more similar to what you're used to. So the master's course that I did at CMU, which was a master's in chemical engineering, actually there was a strong focus on like computers and in chemical engineering. So the idea was that it would be 2 semesters of coursework and 3 semesters of research. So it was a research track. You also have a coursework track, which is just 1 year, but that's more of if you're interested in a job in the industry. But if you want to do research, then you should consider the research track, where you also have enough time to do a master thesis. And so we had 4 compulsory core courses that we had to take during the master's, and they all involved coding languages. So we did a course on reaction engineering, which involved using Python to mainly solve all of the differential equations that you would encounter when you had reaction engineering problems. And then we had a course on mathematical modeling and chemical engineering, where we use MATLAB as the main language. And then we had a course on transport phenomena, where we used COMSOL. And then we also had a course on like process optimization, which was essentially solving a lot of linear or nonlinear equations to try and find local or global minima. And for that, we used software called GAMS. And I'd like to really thank Professor Narayan and also I think Professor Kumaresan for coming up with this course called Computer Applications and Chemical Engineering. I think this is probably one of the most useful courses that I learned because, I mean, over the course of 4 years, we probably do 40 or 50 courses, I think. We might not obviously remember all of them, but one course that I would suggest all of you pay a lot of attention to is this Cache course, because I think it is one of the very few courses that I think is taught in an undergraduate curriculum. And actually, in fact, like when I was doing my master's, I was probably one of the very few in my class that had previous experience in taking such a course that combines chemical engineering and computers. And this was really helpful for me when I did all of these courses because they were exactly the same format. It was using computers to solve problems in chemical engineering. So I think this course is really something that I would suggest that all of you pay a lot of attention to and make sure that you do all of the problems that you are given in the course. So one of the things I'd like to say is whenever you're moving to do a master's, I mean, I know in the US this is the case, but it's probably true anywhere you move to, is that it takes time to adapt to both teaching and learning, but also to the new place and environment, right? And for me, this was a little easier because of the SAP experience that I had. But even then, it takes a lot of time because especially with the teaching and the learning style in the US is quite different from what we are used to. And actually, they have a lot of emphasis on things like quizzes and assignments. So every week, you usually have at least 2 or 3 quizzes or assignments that you have to do. And so typically what you do is you sit with a group and then you try to solve the problem and then you have to write the solution yourself. So you are not allowed to just copy solutions from people. And so I think initially the first semester, everyone finds it difficult. So if you go abroad for a master's and you're starting your first semester, and if you find that you're overwhelmed by all of the coursework, it is normal because it is a huge change and there's a lot of things you have to adapt to. So that's something you should keep in mind, that it might take some time for you to get adjusted to the new environment and the surroundings and the new way of learning. And so it's really important that you have a good peer group. I think you need to have people that are equally motivated and can motivate you when you are down, and you can do the same when they are down. And you can all sit together whenever you have assignments and quizzes. You can try to discuss and come up with solutions. So I think it's really important that you have a good peer group with you when you're taking all of these courses. And I think time management is definitely more important than ever when you're doing a master's program, because you're usually overwhelmed by all of the coursework. And I think the same is true even if you're doing an MBA. You really have to learn how to manage time, because otherwise it becomes really difficult for you to cope up. You might have to spend sleepless nights and you have to forgo on your health and all of that. So I think it's very good if you can, from the beginning, have a very organized schedule that you can follow every day. So you know what you're going to do in the morning, and then try to make sure you sleep enough every day and eat right and exercise and all of that. So I think that's very important when you're doing your master's, and you should make sure that you don't compromise on your health and also your sleep and all of that. So all of this you should really think about before you start. I think for me, I mean, I didn't really have anyone that told me all of these things, but I think this is something that you should know before you start doing your master's. Because we are not used to all of this. Typically, at least I was not used to all of this when I was doing my undergraduate studies. I used to take things as they come, and I didn't really have a lot of long-term planning or organization, but I think it's very important when you're doing a master's. So the first part, like I said, was coursework. And then the next year, I actually spent entirely on working on my thesis. So actually, like I said before, the semester abroad program really helped me decide that I wanted to work on a computational project. So we were given options on projects that we could work on, and I picked on a computational project. And the project was essentially to use ab initio thermodynamics to model solid oxide catalysts for thermochemical water conversion. So, I mean, I don't really want to talk very in a lot of detail, but the idea is essentially to use catalysts here to convert water to hydrogen or CO2 to CO using really high temperatures to create oxygen vacancies, and then you can pass hydrogen or carbon dioxide over, and then they would get converted to either hydrogen or CO. And to me, this was actually a totally new research field, because the idea that I went in when I wanted to do my master's and all that was that I would try to do some research on perhaps like fluid dynamics or something, because I had taken a couple of courses that Professor Naren taught in the final year. And to me, I thought this is probably the area that I can choose, because I'm sort of familiar with at least what it is and so on. But then I chose this particular field. There were some reasons, but I think the most important reason was that it was related to energy, and I was always interested in doing something related to clean energy, and so that was what motivated me to take this particular project. But I think one of the things you can do if something is new is that you can take a related course. So to me, I took a course on molecular modeling, which was taught by my research advisor during that semester. So that really helped me a lot, because I got to know exactly how you have to go about doing things, and because I had no idea about the research field. So this was really helpful. There's obviously other ways you can learn. You can always look up course material online, or you can look at YouTube videos, or you can just read a lot of literature. But yeah, so you have to find ways to learn if you want to pick up a new field. So you shouldn't be afraid. That's what I want to say. So if it's a new research field, I think you just have to make sure that you have enough time to learn. But you shouldn't be afraid to like choose just because you don't know anything about it. And also during my master's thesis, I think I learned a lot of very useful skills. So mainly on writing scientific reports. So I think writing scientific content is like very different from just normal writing. And I think if you do a master's thesis, it's very helpful that you learn how to do this. And you always sit with your advisor and try and give your reports to him or her, and try to get feedback. Because the first time, obviously, you're going to make a lot of mistakes, but with the feedback, you can gradually improve. And also, I learned how to like navigate through literature, because there's really a lot of literature out there, and you should know what you want to look at. You should know the key research, people that are doing the research in the field, and you should be able to search through and make sure you're only reading the right literature, and you're at the same time staying up to date with the field, because there's so much out there. It's really easy to miss some studies, and then you might just be doing something that might have already been done before. And also I learned, I learned a lot of Python, which I thought is something that's, again, really useful in whatever I'm doing. And my advisor was particularly really good at Python. So he made sure that we, pay a lot of emphasis to learn it. And also something called Emacs, which is sort of an environment that you can use that makes doing writing and all of these things really easy. And also some software. So in my case, I learned a software called WASP, which is particularly used in doing these ab initio calculations. So I did learn quite a few things, new things, when I did my master's thesis. And another thing that I thought was very useful was that I attended a Gordon conference. So Gordon research conferences are a series of conferences where they are very focused on a particular topic, and they call the top people in the field. And then it's usually a conference for like a week. And it's in a place that's usually like very secluded. So it's not in a city. It usually happens close to the mountains. And so the people that come there, you're sort of forced to be there. And that's really good, because you can get to interact with a lot of these people that are otherwise really hard to catch. And I think it's great if you're going there as a graduate student, because it's probably the perfect way for you to meet your fellow peers, other graduate students, but also it is just perfect to network. So if you're looking for a PhD position, or you're looking for a postdoc position, I think attending conferences is one of the best ways you can get to know people and to also talk to them. And obviously, you're going to talk to them about your research, so that can either be through a talk or a poster. And I think that's the best way you can pitch your ideas, and you can pitch yourself as a candidate. And then if they like you, it's very likely that they will consider your application. So you should try it definitely. If you're doing a master's and you're interested in pursuing a PhD, you should try to attend at least one conference during your master's thesis. So where you can present your work, and at the same time talk to people, talk to professors that you're interested in doing a PhD. And garden in particular is really good. It's highly recommended. It mostly happens in the US, but you also have a lot of them happening in Europe. And one of the things that I really sort of realized was that I really enjoyed doing research, and I could actually spend nights just thinking about a problem, and I was always excited to look at results from a simulation that I ran. And all of these things I think are very important for you if you want to know, if you want to pursue a career in research and if you want to do a PhD. I think it's very important that you can realize this, that it is something that you're very passionate about, and you're willing to spend the next 4 or 5 years of your life just working on very specific research problems. So I think in that sense, the master thesis was a great way for me to get insights into the field, and also help me realize what my passions and interests were. So unfortunately, I was not able to immediately start my PhD after my master's. I wouldn't say it's unfortunate, because I think it was very useful for me to actually do a job, but I wanted to do a PhD, and I had applied to this program. I'll talk about it a bit about it later. It was a program that is actually funded by Shell and Netherlands, the Netherlands Organization for Scientific Research. It's a PhD program. And I had actually applied to it during my master's, but the first time I applied, I was not successful. And obviously, I was pretty sad, as anyone would be if you're not successful when you apply to something. But then I had this opportunity to actually work at Bloom Energy. So Bloom Energy is a fuel cell company that is in California, in the Bay Area, in the United States. And the company actually works on solid oxide fuel cells, and that was really great for me, because I've always been interested in doing something related to fuel cells. I actually tried a lot to do something when I was actually in Sastra, but things didn't work out. But I was really glad when I got this opportunity, because solid oxides was something that I worked during my master's, and fuel cells is something that I've always been interested in. And so one of the things I wanted to say here was that so the manager that actually recruited me was an alumnus from my chemical engineering program at Carnegie Mellon. So I would really like to stress the idea of networking here. Especially if the person is from the same university that you went to for your master's, I think it's a great starting point for you to start a conversation on LinkedIn or something. Just try to ask them if they have some positions, and whenever they do have some opening, make sure that they think about you. And they're more likely to pick someone that comes from the same university, just because they know the place, they know the people. And so in my case, that worked out pretty well. And again, my experience with Python actually played an important role, because my role here in Bloom Energy was to do a lot with using Python to develop algorithms. So I think that was, again, very helpful for me to get a job. So initially, I was offered an internship, and then I converted to a full-time position. So Bloom Energy is actually a clean tech startup. So it's no longer a startup right now. It was a startup like 7-8 years back. And what they do is they manufacture solid oxide fuel cells. So what they do is they manufacture energy servers, and these energy servers are employed or deployed in data centers across the United States. And so the idea is that whenever there's a grid outage, data centers cannot afford to have grid outages, because then you would just lose all of the data. And so they would use these fuel cell servers as backup. And the idea is that the fuel cell servers are a lot more efficient than a coal-fired power plant. So California was also very generous in giving incentives to a lot of these clean energy technologies, just to encourage people to buy a lot of them. So that was really helpful to the company. And I worked in the advanced process controls team. And the team that I worked in, we mainly developed algorithms to automate the control of energy servers, and also to detect failures. So maybe I can just talk a bit about what I exactly did. So when I joined the team, actually what would happen was we would have these fuel cells across the United States, and we would have a control center where people would just be sitting and then looking at these at the data that is coming out of all of these fuel cells, and then making decisions on what to do. So for instance, they see something and they feel like things have to be changed, or there's something going wrong with this particular fuel cell. they would just dig deep in and then see what's the issue and then try to come up with ways they can do the control. So a lot of it was actually very manual. But you can imagine that if you're trying to scale up and we move to like thousands and thousands of locations across the United States, we can't just afford to have people that are doing this manually. We need a way to automate this whole thing. And my team's main goal was to automate as much control as possible. So we would write algorithms that would help do this. And the way we made our algorithms better was we would actually make recommendations ourselves. Our algorithms would make the recommendations. And then we would have the people in the controls team say if they approve it or not. And then if they did approve it, that was good for our algorithm because it means that it's doing the right job. But if they did not approve the decision that we made with the algorithm, then we would ask them for feedback. And then we would go back and refine our algorithm based on what their feedback was. And so we had a very we had something that was very feedback based. And eventually, I think the algorithm was doing a very good job in automating a lot of things. And actually, at some point, it was even able to catch a lot of things that the people in the controls group would have missed otherwise. So that was a job that I really liked because I felt like it was making a difference to the company. And one of the things that I did also was involved in developing user interfaces to monitor these energy servers. So this was something that was completely new to me because I have done chemical engineering, and developing user interfaces essentially involves using things like JavaScript and HTML to come up with ways you can represent data and ways you can represent plots and things like that. And to me, that was really a new learning experience. And I think that was something that I really enjoyed again and took it up as a challenge to be able to do all of this. So I think the time that I spent, which was about a year in Bloom Energy, I really liked it because it was the goal of the company was something that I connected to a lot. And also the kind of job I was doing was very challenging. And because it was a startup environment, things were very dynamic and we had to work on multiple different things because we couldn't afford to hire a lot of people like big companies could. So overall, I think I was really glad that I had this 1 year of a job experience where I knew how the industry would work. And so after that, in 2016, I actually started my PhD, and I would like to say this quote that I really like, which is that when you want something, all the universe conspires in helping you achieve it. And this is something that was true in my case because I really wanted to get into this Shell PhD program, which I didn't have. I was unsuccessful the first time I applied. But the second time I actually was selected, and I had the opportunity to pursue my PhD in Netherlands at the University of Amserdam. And the whole program, actually, it was called Computational Sciences for Energy Research. And this was actually perfect for me because I had experience in computational sciences and I was interested in energy research. And so again, I think my experience with computers and simulations helped me get this position. And it was something that was really, it seemed like it was made for what I wanted to do because it involved both computers and energy. And the idea of this whole program was that they would train you as a PhD in the Netherlands for 4 years. And then you would have a job in Shell Technology Center in Bangalore. Shell Technology Center in Bangalore is actually the computational hub for all of the research activities related to computations that happen. And so they wanted us to get trained in the Netherlands, and then they would offer us a job once we were done. That was the idea of the whole program. And my particular project was on using molecular dynamics, which is, again, a way you can do simulations. So to look at catalytic reactions in complex environments. So I'll actually talk a bit about this in some time. And again, to me, this was, again, a challenge because I was, again, moving to a different country, actually a different continent in this case, and which was actually very exciting. But at the same time, it also involved a lot of challenges, right? So maybe I can talk now about so navigating through my PhD. So a PhD, like all of you know, is actually a long time. So in Europe, it's usually 3 to 4 years. And in the US, it's a bit longer. It's typically 4 to 5 years. And I think choosing the right advisor is probably as important or even more important than the topic or the university that you're in. I think this is something that you really have to stress on. Like, everyone should know that when you're doing a PhD specifically, having the right advisor is probably the most important thing, because you are doing something where it's unfamiliar territory, and you need the right mentor that can guide you through the journey. You need someone that has been through and can relate to you and can always support you whenever you feel down. And there are a lot of cases in your during your PhD where you might not feel the best. And actually, there's some very interesting thing called, there's a very interesting like a PhD, it's called PhD Comics, and they have some really nice things on life as a PhD, and you can really see a lot of things that you can relate to if you're doing a PhD. So it actually involves a lot of ups and downs, and you should be ready before you start the journey to really be able to know that you will have a lot of successes and failures, and you should be ready to take it on, because you will be working on a problem that no one or very few people have looked into for 4 to 5 years, which is a really long time. So if you try to get into a PhD where you don't like the area that you're working in, you will definitely have a really hard time because 4 to 5 years is really long. And in the end, I think you should probably, or you should actually know more than your advisor in the specific area that you're working on. Because your advisor typically will just give you a problem, and then he will tell you to go and find a solution to it. And he will probably have 4 or 5 other graduate students. They will all be working on different problems. So typically, your advisor will have some sort of a high-level idea of what you're doing, but the minute details is something that only you will know. And in the end of your PhD, in your specific area, I think you should try to know more than what your advisor does, because you have been working on that particular area for 4 to 5 years, right? So you should know the most about that area. And because it's usually a problem that no one else or very few people have looked into, it's not something that you can just go on Google and try to find what the solution is. You really have to spend a lot of time thinking about it and coming up with ways you can solve the problem. And I think definitely it's a very steep learning curve. You have to learn a lot, and especially if it's a topic that you're not very familiar with. You will spend the first 2 years just getting familiar with the topic. And to me, I was able to do a lot of things that I think made things a bit easier, which was that I used to read a lot of literature, and I think this is really important. I would spend a lot of time reading papers and trying to understand what people were doing, what people have done in the past, and what people want to do in the future, and just staying up to date with the current literature. I think that's really important. Also, attending conferences, like I mentioned before, is something you should definitely do. And also interacting with the group. So typically, if your research group has 4 or 5 people, or if it's a bigger one, it has 10 people, that can be graduate students and postdocs. You should definitely try to interact as much as possible with the group, try to present at group meetings, and just get ideas from your own group, because they can give you some really good ideas. And if some of them have probably even been through the same issues that you have had. So it's very important that you interact with your own group and you're not just shut off, trying to solve things all by yourself. And you should definitely be very independent and creative. So in the first couple of years, maybe you can rely a bit on your advisor, so he can just show you some directions. But I think from your 3rd year on in your PhD, you should try to be independent and creative, and you should try to come up with your own problems that you want to solve. And like I said before, you'll have a lot of ups and downs, so you should be ready to deal with both success and failure. Sometimes maybe failure a lot more than success, and which is why it's very important that you have the right people around you that can motivate you, and then you also have the right advisor that can help you whenever you're stuck with a problem. That being said, actually, there's a lot of positive things about doing a PhD. If you really are interested in research, I think there's really a lot of positive things. So one of the fun things is that you can get to travel a lot. So if you're in Europe, I think Europe is a perfect place for that. You can very easily travel within places in Europe. Things are super easy to connect, very well connected by public transport. You don't have to spend a lot of money. And there are a lot of beautiful places around. And also you can use attending conferences as an excuse to travel. I actually attended close to 10 conferences in over 5 countries during the 4 years that I had during my PhD. And one thing I want to say here is that, so in the US, it's typically not usual to travel a lot, probably like 1 conference a year. But in Europe, there is more flexibility. So in my project in particular, we had a lot of budget to go to conferences, and I made sure to use all of that. But that might not be true for a lot of people. So if you do have the budget to travel, I would definitely advise you to do it, to attend conferences, network with people, and also at the same time, you can travel using the conference as an excuse. One of the other things that's again particular to, I would say, Northern Europe is that the salary is really good. You're actually considered an employee. So you will be given, healthcare and bonuses and things like that. And so you can have a very comfortable life as a PhD student, as opposed to in the US, where things can get a bit difficult depending on where you are. Usually your salary is not the best, definitely not as much as what you get in Europe. So that's also something you have to think a bit about. And in my case, I think this whole Shell program is very unique because there were actually a lot of events that were organized specifically for networking. And we were also given free trips to go to India. So it was almost like 2 times a year we were going to go to India during the PhD, which was something that was really good. And also the fact that we were guaranteed a job in Shell, I think it makes things a little less complicated because you don't have to worry a lot about what you will be doing after your PhD, because you have a job, and otherwise it's always in the back of your mind, especially like if you're abroad. Again, if you're in the US, I think it's particularly difficult once you're done with your PhD to find a job if you're an international student. And so if you're in a program where you are given a job after your PhD, I think that's, again, something that's really good. And to me personally, I think I really like collaborating with people. And I really believe in the idea that great science comes with, collaboration. And by collaboration, I mean that you should try to collaborate with people that have complementary expertise. So for instance, if you're doing simulations, a natural collaboration would be to work with people that do experiments. But also within simulations, for instance, I do ab initio or atomistic scale simulations, and I can always collaborate with someone that does more coarse grain or continuum modeling. And so we have some sort of like a multi-scale modeling approach. And so I think that's something to consider if you're doing a PhD, is you should really try and collaborate as much as possible, either within the university or also with other research groups. So I was fortunate enough during my PhD that I was able to actually visit quite a few universities. Again, I think it was because I was in Europe, it was very easy for me to travel. So I actually went to Germany, to Munich, to Barcelona in Spain, and to Cambridge in the UK. And I spent almost every summer of my PhD, I would spend in these universities doing research and collaborating. And also I had some collaborators that were in Switzerland and also within the Netherlands. And I think we were able to do some really good work and publish some really good papers. So I think collaboration is, in my opinion, a very important aspect as a PhD student, that you also have an experience of how it is to work in a team. I think that's important, whether you're going to continue in academia or you're going to move to an industry. Teamwork is always something that is valuable to learn. And I think during your PhD, one of the ways you can do this is just by collaborating with people and working in a team. So this is something I would suggest all of you to consider if you're doing a PhD. Try to collaborate as much as possible. So what I want to do now is maybe just give a very brief overview of my area of interest, which is computational catalysis. So I don't have the time to really go in depth, but I'll just give a very broad overview. So in my opinion, there's 2 main areas in computational catalysis. So one of them is doing detailed mechanistic studies. So what's shown here is a free energy plot. You're probably familiar with this. So it shows the different steps in the catalytic reaction and the activation barriers for each of these steps. And you can see that this free energy profile in particular is quite complicated because there are so many steps involved. And what you can do is actually simulations to really understand why a particular catalyst is good for a given reaction. And this is also something that I did during my PhD. I looked into some very interesting catalysts and then did some very detailed modeling studies to understand why they're good. But the thing here is then you're limited because these simulations are quite expensive. So you can only afford to look at very few catalysts with this level of in this level of detail. The other approach you can take is what's called catalyst screening. So the idea here would be the opposite, right? So what you can do here is you can look at thousands or even millions of different possible catalysts for a given reaction. So let's say you want to look at some electrocatalytic reaction or some catalytic reaction. What you can do is screen thousands of different possible candidates and then figure out which ones are the most active. And the way you can do this typically is in what's called a descriptor activity plot. So what's plotted here on the x-axis is a descriptor. So a descriptor is something that you can measure very easily. So in this case, the descriptor is just, it's called a coordination number. So it's just the number of atoms that this site in red is connected to. And that can apparently be a good way to predict how good the catalyst is. So what's plotted on the y-axis is actually some measure of the activity of the catalyst. So the higher the activity is, the better the catalyst is. And these are typically called volcano plots, and they are called volcanoes because they're based on this principle that was proposed by Sabatier, who is a French chemist. And the idea here is that, so I can show you this plot here. This is a volcano plot. So ideal catalyst is usually on the top of the volcano. So it binds intermediates neither too strong or too weak. So the catalyst should bind the intermediate in an optimal manner, because if it binds the intermediate too strong, then the intermediate will not desorb. And if it binds the intermediate too weak, then the intermediate will not adsorb. And so it has to bind the intermediate in an optimal way. And you can use this volcano type analysis to really look and try and screen thousands of candidates. And this is really where computations can be very useful, because if you think about going into a lab and trying to look at millions of different combinations, it's just not possible. But then with the power of computers that we have today, we can really afford to look into thousands or even millions of different combinations and come up with the ones that we think are really good. And then we can suggest those candidates to people that do experiments, and then they can go in the lab and then test. And then they would only have maybe 10 or 20 of them instead of trying like a million of them, because you have done the job of screening. So in this particular study, for instance, they were able to suggest platinum catalysts for reactions that happen in fuel cells. And then the experimentalists found that this catalyst was actually very active just based on the prediction from simulations. So this is another way you can use computations to do like predictive modeling. And so in my PhD, I actually mainly looked at two reactions that were both related to energy conversion. So I looked at methanol dehydrogenation and water splitting. So they both involve producing hydrogen, which can be used as a clean fuel. And I was particularly interested in catalytic reactions in complex environments. So typically, if you take a catalytic reaction, the environment that it happens in is pretty complex. So for instance, what you see here is a figure of the catalyst that is surrounded by water molecules and also ions. So this is typically how an electrocatalyst would look like. And you also have effects of things like temperature. And in the case of an electrocatalyst, you also have effects of the electric field. And so it's important that you consider all of these effects when you're doing the modeling. And this is something that I was particularly interested in. And what I did was to use ab initio molecular dynamics. So molecular dynamics is essentially using Newton's equations of motion to propagate the system. But then ab initio means that the forces that you have are computed using an electronic structure method, which is computationally very expensive. So these kind of simulations you can't afford to do for very big systems. So you can only look at very small systems and look at very small timescales just because these calculations are very expensive. But they can give you some very interesting insights on what exactly happens with great detail. So that's something I was very interested in. And what we typically do is with these kind of simulations is, in the case of catalysis, we try to estimate activation energies. So again, this is probably a figure that you're familiar with from a reaction engineering course. So having a catalyst can help in reducing the activation barrier, and we're interested in just computing these activation barriers for a given chemical reaction. And we can do that with these very sophisticated methods in great detail with the computational resources we have today. Yeah, so this is actually a movie from a molecular dynamics simulation. So here you have the catalyst, and then you have the reactant, and then it's doing something. So here it's transferring a proton. So this is typically how a molecular dynamics simulation would look like if you try to run it. So close to the end of my PhD, I think close to the end of anyone's PhD, you would have a crisis as to what you would want to do right after you finish your PhD. And in my case, because I was part of this Shell program, I had this job in Shell Technology Center in Bangalore, which was a strong option that I could consider because it was the computational hub for Shell, and I actually learned about a lot of the research that was going on during the annual visits that we had. And also the fact that it's in Bangalore is really good for me because it was Bangalore's my hometown. And to me personally, actually joining Shell was a childhood dream because it was one of the reasons that I took up chemical engineering. So I actually decided in 9th grade or 10th grade that I wanted to do chemical engineering, and I was very keen about it actually. And so to me, joining Shell was like a childhood dream because I was very interested in Formula One. And when I was looking at all of these Formula One races, it was the Shell logo that would appear on like Ferrari. And that was one of the big motivations for me to, do chemical engineering. So all of this was really great that I had this opportunity to go. But then I ended up deciding to actually decline the offer and continue my career in academia because I just felt like I wanted to still continue doing fundamental research, and that I wanted to give a shot at academia and see how much I can go forward. I had the option to choose between like some positions in the US and Europe, but I felt like it was best for me to go to Denmark, to the Technical University of Denmark. So in the end, I decided that I would, do a postdoc. And so I would suggest that, so if you're considering doing your PhD, that you start thinking at least a year or about 18 months in advance what you want to do after you finish. So either you want to do a job in the industry, or you want to, do a postdoc and then try to get a faculty position. So I think it's good to start planning early and start applying to positions. And typically, it's good to always have some options because then it gives you, like possibilities to decide exactly where you want to go. So you can weigh the pros and cons and then come to a decision. So right now, actually, I'm a postdoc at the CatTheory Center. So this is actually a center that is established and led by Jens Norskov. So it's a fairly new center. It was established in 2018. And I really liked the idea of going here because they actually they work on a lot of different areas in catalysis. So they work on catalysis and materials theory, where a lot of the emphasis is on catalyst screening that I spoke about. So they also do a lot of work on fundamental electrocatalysis, which is something that I'm very much interested in. And they also are looking into data science, which is disrupting every field. So catalysis is no different. And so we actually have a division where we have a professor that is very much interested in using data science to look at catalysis. So, and to me, also another reason why I chose to go here was because there was a strong focus on like looking at very challenging problems in catalysis, specifically related to energy conversion and storage. So there is a lot of work done in the center in trying to address issues in producing alcohols, producing hydrogen, producing ammonia, using electrochemical methods mainly, which is something that I've been very interested in. And also, one of the reasons that I chose to go here was because of the strong collaborations that they have. And they're usually a very collaborative, there's a very collaborative atmosphere, which I mentioned earlier, is something that I think is very important. And that is something that they have at the CatTheory Center. So that's one of the reasons that I also decided to, go to this place. And so personally, to me, I feel like being a computational researcher, especially in the area of catalysis, I think there's a lot of exciting things you can do, and it's definitely like exciting times ahead. So this sort of summarizes like my interests specifically, and some of the areas that I think are very challenging. So for instance, looking at very active and selective catalysts for CO2 reduction, nitrogen reduction, and oxygen evolution. These are, I think, challenges that we would definitely like to solve if you want to move to sustainable energy solutions. Another important area in the case of fuel cells is to find non-precious catalysts for oxygen reduction, which is a reaction that happens in a fuel cell. So right now, platinum is the best known catalyst, but platinum, as we all know, is very expensive. So there is a lot of effort in trying to find non-precious catalysts that do not involve metals like platinum and iridium, and so on. And then the other area that I think is very interesting is batteries. So again, I think there are a lot of challenges with batteries. Although it's a more developed field than, for instance, electrolyzers, there's still a lot of issues. For instance, to do with dendrites and dendrite formation, and also electrolytes, ionic conductivity, and so on. And also just looking beyond lithium ion. So lithium ion, in some sense, is limited with the energy density. And so there's also a lot of interest in going beyond lithium ion and trying to find higher energy dense batteries, which can be specifically important if you want to look at electric trucks or electric airplanes and so on. And of course, solar cells, I think, is a lot more mature. I think, already, I think a lot of countries have invested heavily in solar. So I think that's a lot more mature field. So yeah, I think these are some of the challenges that I think would be very exciting to solve if you're thinking of a career in catalysis. I think these are like some very pertinent issues we have at the moment. We don't have very active and selective catalysts for a lot of reactions. And we also have, most reactions, we have very precious catalysts. So that's something that I wanted to also say. So with that, I actually want to conclude. And before I finish, I want to really thank all the teachers I've had over the years, actually. So starting from my high school, these are actually my high school chemistry teachers, Sumana ma'am and Kamala ma'am, and they really inspired me to like chemistry as a subject. And I think one of the reasons that I have so much of interest in chemistry, like right from high school, was because of the fact that I had such great teachers like them. So I really would like to thank them for, being so inspiring and like teaching chemistry with so much passion. And then my undergraduate teachers, definitely. So this is actually a photo that was taken on the last day of college that I still remember quite fondly. And I'm sure you recognize a lot of people that are sitting here. They've probably also taken courses when you are doing your undergraduate course. So in particular, I'd like to mention two people, actually. So Professor Naren, I think it was really great that he joined when we were there in 2011. I took 4 courses with him, and I really enjoyed all of the courses that I took. And I think he's been like really motivating and inspiring to a lot of us, actually. And also, I would like to mention Professor Praveen Kumar. I don't think he's in the university right now, but I really enjoyed his courses. And so he took 2 courses in organic chemical technology and heat transfer. And I still can remember his classes, and he had a very unconventional way of teaching. And I really enjoyed that. And that's something I wanted to also mention. And also all of the research advisors and mentors that I've had through the years, I think I've been very lucky to have people that have been so supportive and motivating. So at KIT, when I did my undergraduate thesis project, I had Professor Ramalingam, who was very supportive and chose me to work on the problem, even though I didn't have a lot of background in the area. John Kitchen was my advisor at CMU. He has always been very supportive, even till today. He's been very supportive and encouraging, and he also introduced me to this entire field of catalysis. So I will always be thankful to him for that. My PhD advisor, Avid John, he has also been super supportive and motivating, and probably like all I could ask from a PhD advisor. So I would also like to thank him. And also right now I work with Karen at DTU. She leads the electrocatalysis group, and she's also been, even though I've just spent a month, she's also been really helpful and supportive. And all of my research wouldn't have been possible without funding from NWO and Shell when I was doing my PhD. And right now my postdoc is funded by the Willem Foundation in Denmark. So yeah, with that, I'd like to conclude, and I would be very happy to answer questions.
Yeah, Nitish, that is very fantastic. You can see the chat window and take up the questions. You can just read the question and answer them. But I would, before taking the answer, it just reminded me of what probably every good PhD advisor will tell their own students when they start or in the early stages of their PhD. That's exactly like it remembered. I remembered when you speak that towards the end of PhD that a student should know more than the supervisor. This is what my PhD advisor told me when I was about probably a year, and I did not thought why he is telling like that. Then he's so that at that time I did not understood it completely, but by the time I finished my PhD, so that's a great sentence. So I actually, while hearing your talk, I texted my PhD supervisor and I said that the same sentence I am hearing now from my student again. So that's very nice.
Thank you.
So you can go to the chat box, read the questions, and then answer them.
So the first question is by Hariharan. So he says, can you please throw light on the process to be followed while doing a literature review?
Yeah, you can stop your presentation so that
sure. Okay. So literature review, I think, there are different ways of doing it, but obviously you need a starting point. So one good starting point would be to ask your advisor, because he must be familiar with the people that are working in the area and, the people that are doing state-of-the-art research. So he can give you some names typically on who is doing the work and who's doing great work in that particular area. And then you can start looking at their papers and then reading and trying to understand. Another great way is to read review papers. So review papers typically, you would be really lucky if there's a review paper exactly on the area that you're interested in, because review papers typically also have references like of the order of 200 or 300, and it's a great way to also look for other references. So you can just look at the references in the review paper, and that can already give you a lot of material to look at. So I think review paper is also a great way. And then another way is, so I think just looking for the key people in the field and then trying to look at their papers, because otherwise it's very easy to get lost. And also I think Google Scholars is great in giving you recommendations once you start using it. I've seen that it can give you some really good recommendations once it knows the kind of papers you're reading. It gives you some very good recommendations on people you can follow, or whenever someone's published a related article. So I think that's also another way to look at literature. And also you can follow some. So for instance, what I do is with Twitter, there are some Twitter bots that tweet on particular topics. So there would be a Twitter account associated to electrocatalysis, for instance. And then there would typically be a bot or some person that is active in that area. They would just share all of the literature that's coming out. So you can just browse your Twitter feed, and then you can come across some interesting papers every now and then. So that's another way. And in my group right now, what we do is whenever we come across an interesting paper, we just share it in the group. so everyone knows about it, and then they also share if they read something. That way we have some idea of like what's going on. And I think that's something that's very important is, like I said in my talk, is to be up to date with literature as much as possible. Okay, so Ariyama says, I would like to use the mic. So maybe, and then Naren sir says, you can ask on the call later. Okay, so I
So
will.
Ariyama, if he wants to talk, he can talk. Ariyama, if he's able to, I mean, he wants to directly ask. Yeah, Ariyama.
Yeah, am I audible now, sir?
Yes,
Yeah.
Ariyama.
Hi, Nitish. I'm Ariman, and I'm currently living in Emilia-Romagna, Italy. I'm a first-year master's student at the University of Bologna in Italy.
Okay.
I would like to inquire about the Erasmus Plus traineeship program which you have all across Europe.
Yeah.
Actually, I wanted to come to DTU. For the Erasmus Plus Mobility Program. Is it like the lab which you are working on right now? Is it like purely research-oriented lab, or like do I need to take the coursework as well as research as part of the program?
Maybe you can finish and then I'll answer.
Yeah, no problem. Yeah, you can answer.
Okay, so I think I'm not exactly sure about the exact structure of the Erasmus program. As far as I know, when I was in the Netherlands, there was an Erasmus program that my group had was involved in, and there I think the idea was that you would take some courses and then you would choose to do a final project in a university. And so in the Erasmus program that I was familiar with, it was a collaboration between a university in Italy, the university in Netherlands, and one more, I think, in France. And so the students would take courses in each of these universities. And then in the end, they would decide where they want to do the final master thesis project. So I think it involves both coursework and doing research. And my center is only research. So, I mean, of course, we have professors and they have to take courses, so they do that. But the center itself is just focused on research only. So,
as a tidbit information, the famous RKS equation, the Rendley-Kwong-Suave, the Giorgio Suave in the RKS equation was originally from Italy, and my professor worked under his RA. He was now in DTU, I heard. RKS.
Oh, really?
Yeah,
okay.
he's now in DTU, I heard.
Okay, interesting.
The Giorgio Suave of the RKS equation. That's a kind of a tidbit information I would like to pass. And the third one is, and the third thing is regarding the molecular simulation, because as I'm in the first year of my master's, there is a course on molecular simulation where we use this software called MAPS from the company called Synomics. I don't know if you are
familiar with that.
It's not open source as this Gromax, but it's a private company. Which is, I have this one question, like what I personally feel taking the course is whenever where the professor comes and like says you apply this force field and like you run the simulation, the software does everything for you. Okay, like from the statistical function to like the diffusivity constant, everything it does. Okay, don't you think like we as engineers with our background are not so inept in understanding the deep underlying meaning behind all those computational procedures which that LAMS does, or the statistical mechanics part? Don't you think we lack, and without that it's just useless to like just run few commands on the software?
Yes, so true. I think so. There's two approaches, right? So one is that you use the software as a black box, and then you just feed in whatever you want, and then software does some stuff, and then it throws out the results.
Yeah,
and then you look at the results.
You don't know what like did I even enter the right data, or whether the data I'm getting is right, or like what is really happening behind the lamps is the question I wanted to ask. Your views on that, because as a first year student, I feel that it's pointless, just to like run few such commands.
You should definitely, So in my case, what I did was when I started my PhD in doing molecular dynamics, we actually in our group, we organize a very nice winter school that happens every year, which is on understanding molecular simulations. It's based on a book, and we have professors that come and talk really about statistical mechanics and all the ensembles and all the the equations that are behind all of the molecular dynamics codes, like just starting from very basic equations going all the way to complicated things towards the end. So it's a 2-week winter school. And I think these are things you should probably do before you start doing something. For a master's, I don't know if it's if it's very easy to do something like that, because with a PhD, you're going to invest the next 4-5 years doing this. So you might as well spend enough time. Yeah.
The view I have is like, okay, the professor comes and says, okay, apply this force field called Cornell or like Dryden, whatever. The force field, there are a set of force fields which are there to apply. Okay, fine. I don't even know what those force fields are and how they are derived or what are they. In fact, it just asked me to apply the force field, like input these temperature and like density values. You get the diffusion constant. That's it. Done. And that's how it's done here. I don't know how it's done in DTU or the Netherlands, but in Italy, it's done like that. And I feel like, what is the main?
I agree. I completely agree. In my opinion, I think it's also very important that so you shouldn't get too caught up in all of the math and all of that like behind, because then you will just either get very bogged down by a lot of the math equations and all that. I think what's very important is you understand the concept. You don't need to necessarily know, the exact equations and all that, but you at least can understand why you're doing the simulation. If you're doing something, why are you doing it in a microcanonical ensemble? Why you're doing it in a canonical ensemble? At least, things like that for beginners would be like really good. So you know exactly what you're doing. And if you're really interested and you really want to go into the details, I think you can definitely do that because in your PhD, you have enough time. So you can definitely spend like during your 4 years, every day, just spend 10-15 minutes, trying to understand something in in depth, if you're really interested in that topic.
Okay, thank you so much, sir. I'm done, sir. Thank you so much.
Okay, so thanks. So the next question is by Lokesh, and he says softwares used for molecular dynamics are expensive. Okay, so I'm sorry. So by expensive, I mean computationally expensive, not like expensive in terms of money. So all the softwares that I've used right now, so I use something called CP2K, and it's entirely open source. And also the code is available online. It's open source and free. And it also has a community where you can ask questions, and it has some manuals for beginners and all that. So when I meant expensive, I meant that in terms of computational time and not the money itself. Yeah. But then there are, of course, expensive softwares. For instance, WASP is a paid software, which is quite expensive. So in that case, your university or your group typically has some licenses that they can give you. But please make sure you don't try to, download things that are from the internet and then use them. And then if you write papers and they find it out, you can get into a lot of trouble. So that's something you should be aware of. And then the next question is, could you elaborate more on automation technologies you used in Bloom Energy? Yeah, so automation, I wouldn't say it's automation technology. It's more like algorithm. So essentially, we had a lot of data that we stored that was coming. So every second, our fuel cell server would send data. We would collect all of that data, do all of the analysis, and then have the algorithms come up with suggestions on what to do. So for instance, if we find that some system is showing early signs of failure, our algorithm can detect that. And then we will immediately notify the people in the controls team that can then take the action to do whatever they prefer. Or in some cases, the algorithm will just automatically take the decision and then make the change. So these automation technologies here, essentially, they're basically algorithms which are typically written in Python to do all of the data analysis. And then we also have things like Hadoop and Mongo and all that to store all of the data. And then all of the analysis is just done by the algorithm. And then we have these user interfaces that I was talking about that I was involved in developing, where we would just give out the results of these algorithms in a way that it's easy for people to interpret. So Rahul asks, what are CFD softwares you could suggest with helping for masters? Well, I'm not very familiar with CFD, but as far as I know, there's OpenFOAM and COMSOL, but then I'm pretty sure like Naren sir and other people that are in CFD probably have a better answer to this, because I've not done any work on CFD, so I unfortunately cannot answer that question. But yeah, maybe so. Naren sir, do you have something to say on this?
No, it's okay. You continue.
Okay, yeah. Okay, so Neeraj says, generally when pursuing PhD, I've heard people say a topic is the one that is of utmost importance, but your suggestion is intriguing. How do you identify who is the right professor? Yeah, but again, I think that's a bit difficult. I mean, so because the only way you can gauge is when you have the interview, right? So you typically, when you're interviewing for a PhD position, you have like either a Skype interview, or you are also able to, in some cases, personally visit the group. I mean, of course, if you can visit the group personally, that would be really good. So what they typically do in the US is, if you get an admit, they have something called a grad recruiting weekend, where they'll just call all the people that they've admitted into the graduate program, and then they will call you for 2 days to their university, and then you can just interact with all the different professors that are doing different, working on different areas. And then you can interact with people in their group and then try to get a feeling of, how the group is and so on. So that's definitely one way you can do it. So you can attend this grad recruiting weekend if you're in the US, and then target a particular group that you're really interested to work in, and then talk to that professor and the people in the group. I think it's also very important to talk to people in the group, because they can give you like firsthand knowledge of how the professor is and how he does things and so on. But if it's just an interview, which was what it was in my case, what I tried to do was to try and contact some earlier PhDs that had passed out with the same professor, and then send emails to them and try and talk to them and understand how the professor is and things like that. So that's something you could try to do. But at some point, you should also just be lucky. So another thing you should probably also look at is how frequently is the professor publishing. I think that's also very important, because you could be stuck with someone that's towards the end of the career, maybe, or I don't know, at some point, who have lost motivation to publish. And then as a young scientist right now, I think it's very important that you publish. I mean, even though it's not very healthy, that you at least try to publish 2 or 3 really good papers. So you have to look at the publication track record of that professor and see if he's actively publishing papers. I think that's another very important indicator. Yeah, and I also, one of the things that I was very disappointed was that a lot of the professors don't really keep their research pages up to date. So they might have a research page, but that might be research that they were probably doing 5 years back. And that happened to me when I was going to CMU, because I had some people in mind, but then they were really not doing the research that was there in the research page. So that is something that you should also be aware of, and make sure that the professor is really working on what you're interested in, and that the research page is up to date, or at least you can try to ask the professor exactly what they're working on right now. And then Rajsri asks, there are so many simulation software, CFD and other fields. Do we need to specialize in every software or specific ones? If so, how to choose which software to follow? Yeah, I think this is a good question. So in my field, for instance, with ab initio, that's either doing DFT or molecular dynamics, there's actually so many softwares you can use. My personal preference is always to look for a software that's open source and free, and a software that has a strong community, researchers, and also a strong online forum, because that is really helpful when you have questions or you're stuck with something very particular. You can always go to the forum and ask a question, and people are usually very helpful and they can answer you. So that's something I would always look at. And then beyond that, your advisor typically can also suggest you, so depending on what you do. So some groups have their own in-house code. This happens a lot with people that do fluid dynamics. I know, for instance, my friend who's at TU Eindhoven, who works in a CFD group, his group has an in-house code that they use, and they don't really look at commercial softwares like ComSol or OpenFOAM and things like that. So that again depends on the group you're in. So either your advisor suggests on what software you have to use, or you pick the software that is best suited for your application, right? So in my case, for instance, if I want to look at molecular dynamics and I want to look particularly at ab initio molecular dynamics, then there are not many softwares. And so my options become a little restricted, and then I can choose the software that best matches what exactly I want to do. Because different softwares have different features and are known for different things. So you can pick the software that you think would best suit the problem that you're trying to address. And it would be great if that software is also open source and free at the same time. So how challenging, so Professor Naren asks, how challenging was the PhD interview? Yeah, so the way that the whole thing worked was we had actually given multiple interviews, and then the professors would write their options and we would also write our options, and then they would do some sort of matchmaking. So in the end, I actually interviewed with 9 professors, so 9 different professors in different universities in the Netherlands offering the PhD. And so actually, in the hindsight, I feel like it was too many interviews back to back. But the interviews in general, they were trying to test. So different professors had different approaches. Some of them were trying to test basic skill fundamentals on. So let's say you did DFT, for instance. They were trying to understand if you know DFT, what DFT does, what are the limitations of DFT, why do you think DFT was the choice that you used for the systems that you were looking at, and things like that. Some professors talked about the research that they were doing, and they were trying to understand from you if you had something to say. So we were also sent the proposal beforehand, that the proposals that were funded. So we had an idea of what exactly the project would be. So they were trying to test if we could just read the proposal and then come up with probably ideas that we could look at if we were given the option to start the PhD. I think that's also a great thing. Is if you can read a proposal and already like come up with ideas that you can start when you do your PhD. I think that's also really nice if you can do that. And then also Naren sir asks, can you give perspective on why a typical student in India is not very open or welcoming to self-learning styles, whereas one adopts when moving to or compelled when moving to universities abroad? Yeah, so I think it's because of the fact, like how we are used to learning, like right from school. I think all of us are used to one way of learning. And I don't know, I don't want to say one way is right or wrong, because I don't think I'm in a position to make any comment in that regard. But I like the idea of how they teach in the US, where I also attended one of these courses where the professor would give you the material beforehand, and then you would have to read the material and come to the class, and then he would teach, and then you could ask questions. So you already know what is going to be taught. I also really like that idea because then you already know what's going to be taught, and you can also frame questions in your mind when you attend the lecture. So I really believe that self-learning is really good. So if you can, because I think that really forces you to understand the concept and you really think about something if you cannot understand it the first time you read. And I think that's not typically what you would do in universities in India and probably even other countries that I don't know about. But so I think in Sastra, like one of the things that's probably good with this whole COVID situation is that I guess now you guys are having like open book tests. And in my opinion, that's good. I think open book tests are great because it's like saying, okay, you know what? I think this happens very frequently with IITs, right? It's like, okay, I give you the book. I don't care. You can look at all the formulas and everything that you want, but I will still make sure the problem is challenging enough that it doesn't matter if you have the book or not. Right? I think that's really good because there's no point in like memorizing formulas as long as you have access to them, right? Because in real life, even very simple things, we are always trying to Google and understand. And this doesn't matter if you're a PhD or a postdoc or a professor. So you always have access to like formulas or information or whatever. I think it's what's more important is given a problem, you know which formula you have to use to solve the problem. Do you know why you're using this particular formula to solve the problem? I think that's more important than memorizing what the Ergen equation is or things like that. I think that should be really emphasized when you're teaching. So I think open book is a great way to do that, I think, because then you're saying, okay, you have the book, you can get whatever material you want. Maybe you can also have a cheat sheet, but then the problems will still be challenging enough that it doesn't matter if you have the book or not. You're really forced to think. I don't know if that answers.
That's nice. Tomorrow I have a Google class.
Yeah.
And it is going to be on Ergen equation.
Okay.
Yeah. So I think Hariharan, you have to put your phone on mute.
No, yeah, I think I wanted to ask him a question actually. That's why.
Yeah, yeah.
Yeah. Hi, Anna. This is Hariharan, and I'm doing my master's of chemical engineering in Australia. So I wanted to know like what is the advantage and disadvantages of doing a PhD through a company, and is it like even though you're doing a higher studies in PhD and you're then going to work for a company, right? So is it like more like an doing an industrial job or like it is research oriented? I want to know after you finish your PhD when you're working with a company, will it be more like an you'll be working like an process engineer or like more research oriented? And what is the scope of jumping between companies after you complete some experience with the company through which you did your PhD?
So with regards to like doing, so I think you were also asking about doing a PhD with a company, right?
Yeah, through a company. Yeah.
Yeah. So in the case of Shell, actually, they were very hands-off. So all the projects were very fundamental, which is one of the main reasons I took it, because I'm more interested in solving problems that are fundamental and might not never see the light of the day in an industry, as opposed to doing something that's very like application oriented. But I know, for instance, my friends that were in like industry-funded PhDs, where they were given very specific problems that were of immediate interest to the industry. So there you have a clear goal, and then the company is also very much invested because they want to know what answer comes out. But in the case of this particular program that I was in with Shell, they just wanted us to gain the skill sets. So they were not very much interested in the problem we were looking at, as long as we were learning the techniques like molecular dynamics or whatever. And with regards to like working in a company after your PhD, so in the case of Shell, you would join as a graduate researcher and like as like a fresher, in the R&D team. And what you would be doing is you would be working in a group. You would be reporting to a manager who typically has a PhD and who's been has a work experience of 7-8 years. And initially you'll be put on a project, and then you will typically it's like a 3-year graduate program. You'll also have to take some courses, and then once you do that, you will be promoted. And they have a very typical track for people like graduate students that you follow. So the only difference between doing a master's and joining Shell versus PhD is, I think if you do a PhD, you're most definitely going to join a full-time research, like an R&D group. While if you're doing a bachelor's or a master's and then joining, there's more flexibility on like what group you want to join. So some companies also have like a 1-year rotation where they put you in different groups across, and then you can choose in the end the group that you like the most. You just join that group. So there's definitely like more flexibility. But once you finish your PhD, I think your options really narrow down, which is another reason you should think about it, because you become really specialized in one particular area. So your options narrow down quite a bit compared to if you just have a bachelor's or a master's. So that's also something you should be prepared. And you shouldn't realize at the end of your PhD, most people don't want to hire me because I have some very specific interests, and so they're less interested in hiring me and things like that. So that's something you should keep in mind. And then I think you also had another question. I forgot.
Yeah. So what's the scope of jumping between companies after you after certain experience with Shell? Or
yeah, so with Shell, I think as far as I spoke to most people there, it seemed like people were just there for 20 years. Like they just started with Shell and they wanted to retire in Shell because they just like the company so much. But I would imagine if it's more of like a startup company, then it's most likely that people are there for 3-4 years and then they switch. So it really, I think it depends on the company. But in general, I think the attitude that I guess people from our generation have is more. I think it's very different from the attitude that people.
Sorry to interrupt, but I think you've misunderstood the question actually. Like I'm not talking about all employees. I'm talking about like for if you have finished a PhD, right? So now suppose you were working for Shell, and after a certain period you want to move out of the company or look for another job. What is the scope for that? You did a PhD through for a project that is much related to Shell. Right.
Yeah, so that again depends, right? So I think the idea is like at least with the project that I did, that they want you to gain the skill sets, and then it doesn't matter like what you apply that skill set to, because you can learn CFD or molecular dynamics, And then it doesn't necessarily have to be towards a particular problem. You can use molecular dynamics to look at catalysis. You can use molecular dynamics to look at batteries. You can use molecular dynamics to look at polymers. So it doesn't matter as long as you learn the skill set. And I think that's very important in your PhD. I think what's most important is you learn a particular skill set and you're very confident in using it, as opposed to looking at a very particular system. Or again, I think that depends a bit on the PhD. So there are some projects, for instance, that shelf funds where they're very specific in what they want you to do. Then I think it becomes difficult when you want to switch. That's true. But if you so that's when you should make sure you learn some very general skills, like learn things like data processing or molecular dynamics or things like that. So it doesn't matter like which industry you're in, you can always benefit from those skills. I think that's something you should also keep in mind.
Yeah. Okay. Thank you.
Yeah. Thanks.
So that's nice. So any other questions? I think we are very close to more than an hour now. Okay, so maybe I'll just ask the usual question, which probably is useful to the present students. Like, what should they focus when they are in their undergraduate? It could be in terms of knowledge component, skill component, or it could be in terms of preparation of their application, or which universities they should scrutinize for joining their MS, PhD, or typically they have a question of is America is better, or Canada is better, or it's X country better, Y continent better, something like that.
Yeah, I think, I can talk from my, what I experienced was, so for me, what was most important was to make sure, the first thing that I wanted to make sure was I had good grades, and I had I'm like through the years that I was there. And another thing was that there are some subjects that I really liked, and I made sure that I was, I could learn as much as possible, because it's obviously very difficult to have interest in all the courses that you've been taught in chemical engineering, right? Typically, you are interested in a few areas, and I think that's totally okay. Like, you should just make sure that you also, of course, you learn all of the courses that are taught to you, but everyone has an inherent interest towards certain courses, and I think that's completely okay. And if you think that is something, some courses, like one course is really interesting to you, you should definitely spend a lot more time. And one thing you can definitely do is spend your summers usefully. We have, Sastra does not have a long summer break like other universities do, but it's good enough for you to do some sort of an internship, either in an industry, or if you want to do things like I think the Indian Academy of Sciences has a fellowship program. All the IITs have a fellowship program. I think these are great things you can do during your summer. And it also really helps you when you apply to graduate school, because you can show them that you're really interested in research, or you're interested right through your undergraduate degree. You're not just doing it because you want to apply to a master's program, but you've always been interested in research. And I think that's very important to show. And one of the ways you can do that is by spending your summers in a very useful manner. And I think for me, I started thinking about higher studies towards the end of third year. So maybe around fifth or sixth semesters, when I really got serious about thinking about where to go and all that. In my mind, I was clear that US was where I wanted to go, because, most good, I wouldn't say good universities, but most universities that you've heard of, are in the US. And in my case, I had a lot of family in the US, so it was obvious for me that I wanted to go there. Although I had some thinking, I also thought about Europe, because I had gone to Germany and I really liked the experience there. But so I think it's really difficult, in the beginning to, when you're doing your undergraduate, it's really hard to figure out where you want to go, which continent you want to go to. And I think this alumni series is a great way for the current students, because I think you have people from different continents and different countries talking about their experiences. So I think this is a great way they can figure out what they like best, which country seems like a good option to them. For instance, if you're a workaholic, you should definitely go to the US. If you are more chilled out and you like work-life balance, I think Europe is probably the best place, because the standard of living is really good, and people don't work beyond 5 o'clock. Fridays, 2 o'clock, everyone is gone. Weekends, no one even looks at their emails. All of these are completely opposite to my experience in the US, because in the US, depending on which group you're in, obviously, people are replying to emails in the night at 12 or 1, even on weekends. And, people are working in the lab through the night, So I guess, yeah, like you should figure out what like your personality and like what country would fit best in that aspect.
So that's very nice. Good tips and guidance that you have given, and it's very nice to the juniors as well, right? So any other questions? I think it's already, we have crossed a lot of questions. If there is anyone, or okay, so if there are no other questions, maybe so I would ask Venkatraman.
Yes, sir. I'm here.
Yeah, so you can give a remark of closing comments on how was your classmate today.
Okay. From college. All right. So yeah, Nitish, of course, he was an amazing friend and a very intelligent person. He was smart, and also he enjoyed spending time with us. Like, and he'd be the first person to say, "Let's go out and eat." He used to hate mess food so much, and we have a lot of such memories there, going to Punjabi Dhaba and having dinners there. And apart from that, academically also, he knows when to study and when to give his spend. How to split his time to various things, and he's actually pretty good at that time management as well. And he was kind of very focused, and he found intrigue in the smallest of things as well. That's actually very difficult. A lot of people would think that something where we want to work on may not have immediate application, and probably would not choose that. We would always, we think the world is so fast paced and we want to do something or work on something which has immediate application where we can actually realize it. But then I think Nitish enjoyed in what he did. He appreciated a lot of things, even the minute details, and it doesn't really matter if there's going to be an application the next day, but in the long run that contribution is very important. So that is what I think Nitish believed in. That's actually a really good way to pursue research for those who are interested in research. And particularly regarding his talk today, his journey from Sastra till here, the way he discussed everything was amazing. It was actually very, very motivational. It's very important. Like for our batch, probably we didn't have, we didn't get an opportunity to discuss such things with our alumni, but this must be really helpful for people currently in Sastra and those who are doing masters. If they want to go on to a PhD, so this talk would be very, very useful.
Yes.
So congrats,
Thanks,
Nitish, on your
yeah,
as well.
Thank you very much.
I mean, can I?
Yeah, Neeraj, yeah.
Yeah, sure. So yeah, Nitish, it was a beautiful talk, like really well structured through and through. And I think, one thing is talking in detail about your PhD, but I think you handle it very well. Like you spoke more about the journey and like handling different cultural aspects, etc. Which I think was like something that is needed for students at least, like because during my masters and even right after it, I was like, one of the things that I had in mind was probably pursuing a PhD, and I was literally throwing darts in the dark, right? So I really did not have any sort of guidance, and I was just trying to do it on my own, and it was very difficult. But this talk, at least for all of you students out there, it should really be helpful, and I would urge you to get in touch with him personally if you guys need to, in order for you guys to figure out what needs to be done. This is irrespective of just Nitish. You can get in touch with any of us if you guys need any guidance at all. And going about it, like the college aspect, yeah. More. I think Venki touched upon the basic things, like basic characteristics of Nitish. But one thing that I personally, and I think Ara would also agree with me, that he was probably one of the best teachers that were there. Like like when we had exams the night before, and probably right before the exams also, he was like, I think he helped us a lot there, and he was probably the best teacher. In our peer group at least. So that's something that I want to share. And given that you're pursuing a postdoc and you're getting into academia, I wish you all the best, and you're probably going to be a very good teacher that your students are going to appreciate. And yeah, thanks for taking the time for this talk, and it's pretty insightful.
Thanks a lot.
Yeah, good.
Thank you.
So that is very nice. That's very nice. Yeah, anybody else wants to speak? You can just unmute and just speak. Anybody else? Yeah, so
Sorry,
that's okay. So you have a problem with the mic, Hariharan. You can send
sorry,
an
just
email.
one last point to add. So the very fact that he mentioned about all the faculties says how much he values their inputs, etc. I think that's one of the qualities that will make him a good teacher as well.
Fantastic. Yeah. So I think it's only a matter of probably a few years or maybe months. Like maybe we will have a set of lectures on molecular simulations, dynamics being thrown away. Now you need not come physically. So from probably Denmark, he can take lectures, and I think it's not far away that on a Saturday he can, or a Sunday or something, he can start really taking lectures. And as he's been focused, it's not everything is for application, marks, grades, and everything. It's just for the sheer joy, sheer cherishment of knowing a concept, understanding and concept, and that I think he stayed. What is very impressive is almost now it's a decade, or it's close to a decade rather, but he has not changed in his speaking style. He has not changed in the way he approaches. Everything is still fresh. And I just want to add, I think he was very good in maths, if I recollect. I don't want to quote an incident, but I think he got his grade also back by the process S in his third semester, if I think. That's before I joined, probably. So that's very nice that he's focusing on fundamental science, which is also very important. It's not like everything that we do today, as Venkatraman pointed out, has to have an immediate application or a foreseeable application. We can still do something on a topic that we really cherish just because we want to understand it more, because we are curious enough to more. Okay.
Exactly. Yeah. I just want to give the example of, for instance, like gravitational waves. So when Einstein developed the whole idea, he had no belief that this would be ever like detectable with experiments. And then in 2017, the Nobel Prize for Physics went to the people that worked on the gravitational wave detector, and that just goes to show how much of an impact you can have if you just do like even fundamental science. You might not see any application even in your lifetime, but I think eventually it will definitely have some use somewhere. I think, which is why it's also important that all the governments like spend a lot of money, or not a lot, but at least give money to working on very fundamental problems.
Yeah, so that's very nice. So what is important is we should cherish what we are doing, and not because somebody else is telling that field is good, this field is good, this field has so many applications, or this field has so many industries, etc., etc. The prime motivator is, am I loving what I'm doing, right? Am I finding peace? Am I finding happiness in the topic that I am particularly interested in? So that is actually the driving thing, and I'm very happy to see that in Nitish, and he's very confident, because I am not sure if somebody else or most people of this generation or of his age, whatever it may be, if you have a very lucrative job in a dream company, it is not a dream company just by the size, it's a dream company also by their virtue, in terms of they literally not treat everybody as their employees, but they own their employees, they nurture their employees very well. Despite having such a very lucrative offer, he was very keen on going to learn something fundamentals, and he was not worried about, oh, what will happen to my job or where I will land up and everything. So that is something, a very clear-cut message I want all the juniors who are there now and who will also eventually see in YouTube later on to take from Nitish. Thank you, Nitish. That was a very wonderful talk, and I'm very happy to have you here and sharing your learning. Thanks to all who have participated.